Welcome to Brain Vision.
Okay, so for part A of this question, we want to find the rate of heat flow through a solid wooden door. And keep in mind that there are air films on the inner and outer surfaces of the door that have the same combined thermal resistance as an additional 1.8 centimeters of solid wood. So when it's asking for the heat flow, we want to think of heat current. There's a flow of heat from outside, inside, outside, depending on the temperatures. So in this case, we have that's given to us that the temperature of outside is minus 8 Celsius, temperature of inside is 20 Celsius. So really all we have to do here is use the equation for heat current, which is H equals K, which is thermal resistance, or thermal conductivity, times A, which would be the area of our door, and times TH, so the hotter temperature, minus TC, the colder temperature, and that difference is divided by L, or like the width or the length at which the heat will travel from. Since we're talking about a door, that length is actually going to be the thickness of the door. So you can imagine kind of the cold air on the left side of the door, outside of the door, and that hot air on the inside. It's going to travel through that door's thickness. Okay, so the thing I want to keep in mind is what is A and L? Because we already have what K is. We know the hot temperature is 20 Celsius and the cold temperature is 8 Celsius. But what is L and A? So A is just going to be the area of the door, which is 2 meters times 0.95 meters, the length times the height of the door. So that's just going to be 1.9 meters squared. Okay, and the length, we know the width of the door is 5 centimeters, right? That's given. But they give us this extra information about these air films, and that's why we have to make sure we read all of the given information, because this adds an extra 1.8 centimeters of thickness. So these air films act as about 2 centimeters of extra wood that's on the door that's not actually there. It's just the filters that construction people put on the doors to help trap the heat better and kind of help the transfer of heat in your home. So 5 centimeters plus is 1.8 centimeters, and that's going to be that length through which the heat's going to try to move through. So all we have to do now, plug in our values and solve for this H. We'll do H, we'll call this H sub door. That was not very well written. We'll do, for simplicity's sake, H sub D. So that's equal to times K, which is 0.12 watts. And while you're writing this out, keep in mind like what you want our units to be. So we're talking about heat flow, and heat is obviously energy, so that'll be in joules. But we're talking about a current or a flow, that's over time. So we want our units to be watts. And times the area, 1.9 meters squared. And times the temperature difference. Again, we're doing a temperature difference, so you can use Celsius or Kelvin, but since our thermal conductivity is in Kelvin, we should use Kelvin. So that temperature difference is actually going to be 28, because we're doing 20 minus a positive 8. I'm sorry, 28 minus a negative 8. So 28 Kelvin divided by our length in meters. Again, keep SI units. So 6.8 centimeters is 0.068 meters. If you plug and chug that out, we'll find that H sub D, or this heat flow, or heat current through the door, is 93.88 or 93.9 watts. Okay, great. There's part A done. Okay. So for part B, we would now want to find By what factor is the heat flow increased if a window is inserted into the door? So essentially we're doing the same type of equation, but now we have two materials that make up our door, the new glass window and then the remaining area of the wooden door. So essentially we're going to have two heat current values that I'll add together to get a new total heat current value for this new door. So let's first find the heat current to the glass. Let's say Hg. Okay, so again, they gave us a new thermal conductivity, which you can also look up where it's in the book. We'll call that K sub G, right? And then what's the area of the window? It says it's 0.5 by 0.5. So that's pretty straightforward area. It's 0.5 squared. Same temperature difference as the outside. Just writing the equation here again, just so there's no confusion. Right? So the thing that does change is our length. And we know that the width of the window is 0.5 centimeters. That's given. And there are new air films that add about 12 centimeters thick glass. So that's how we, again, like what we did in part A, we're combining these two lengths that are given to us to get the total length through which the heat will flow through. Okay. Let's go back up. Okay, so this H sub G is going to be equal to thermal conductivity of glass, which is 0.80 watts per meter Kelvin. What's the area of our glass window that's inserted? It's 0.5 squared, or 0.25 meters squared. Again, same temperature difference, 28 Kelvin. And as I mentioned just a little bit ago, this new length is what you have to keep out for, or watch out for. So it's really going to be divided by 12.45 centimeters. If you combine your 0.45 centimeter width of the window and that 12 centimeter air filter, convert that to meters, you get 0.1245 meters. Okay, we have our full expression. If you multiply that out, you get that H sub G is equal to 44.98 watts. Okay, I'll underline that. We'll need that in a second. So now we have this. This is just the heat current through the glass window, the tiny window that you put in your door. So now we have to find what's left. So the window took out a chunk of the area that's wooden, as it was in part A. In part A, it was a completely wooden door. Part B, we have the window square that takes out 0.25 square meters of the wooden door area. So really just have to adjust our heat current equation slightly to change the area. Everything else is the same. Same thickness, same everything, just a different area. So we want to call this, we'll do HD prime because it's a new wooden door here, okay? So then we're going to have K of wood, this new area of the wood. Again, let's prime that just so there's no confusion. It's a different area. It's still going to be times the same temperature difference, TH minus TC. And over that original length we had in the first part of the question. Let's write out the values and then solve it real quick. So again, this is 0.12. Again, this is all, most of these values are given. Watt meter per Kelvin. This new area. So it's going to be, the original area is 1.9 square meters. Subtract the 0.25 because of the window, you get 1.65. Square meters. And times the same temperature difference, 28 Kelvin. And this length of 0.068 meters. Again, same thickness as our normal wooden door. That hasn't changed, just how much of it, or how much area there is. Multiply that out, you get 81.53 watts. Perfect. So now we need a total H, right? Because we have the heat current of the glass window, and the heat current of the door that's left over. So we're going to say the H total is just going to be equal to the addition of these two separate heat currents, which gives us 126.51 watts. Okay, so there's that. So to get the factor, this heat current factor, by what factor is the heat flow increased if this window's put in? All we have to do is just divide these two total heat currents from part B and part A. That gives us our factor. So all we have to do, because all it's looking for is a ratio between the two currents, the two heat currents. So all we're doing, H total over that H from part A, which is, we just called it H, divide those two numbers. So you do 126.51 divided by 93.9, and you will get 1.347 or 1.35. It's good enough, round off. 1.35. 1.35 is our factor. And there you go.